Good morning, dear students. Once again, the students who are in touch with me for the long time, they identify me, and the students who are new, sometimes new students are added. I just want to introduce them myself. I'm Seema Tamrakar, the PCT chemistry of KOHLRAUSC'S Vidyalaya number 2, Riva, and I'm assisting you in your online learning, the learning from home. And in my previous classes, we have discussed some of the concepts of the electrochemistry. And today, I will continue the chapter and I will come to the another important aspects of this chapter. The importance of this chapter is that it is applied for the industrial purpose and as the source of energy as well. And because of this chapter is important not only from the examination point of view, but when we study what is the role of chemistry in our daily life, while we study the subject chemistry. It is the part, it is the application of the chemistry in our day-to-day life. In my previous class, the class just one day before, I have discussed the basic terminologies. The resistance, the conductance, specific resistance and conductivity. And I'm going to continue with the same only. I'm just going to give you a quick review of the topic we have studied earlier. Resistance means the obstacle, right? How the flow of electric current is obstacle hindered by the medium, right? Nothing is 100% conductor. Conductor may be good conductor or poor conductor, but 100% conductivity is not possible. And this is just because of the resistance present in the every medium. The inverse of that, the support, the easiness, the helping of flow of charge from one point to another, that is the conductance. Inverse of the resistance, it is the conductance, and the resistance was dependent upon some factors. There were certain factors on which the conductance of the system, the conductance of the cell, or the conductance of even the metallic wire also depends upon. And two important things were there. First is the length, and the second one is the area of cross section. In the case of metallic wire, the length of the conductor, and in the case of the electrolytic solution, the distance between the electrodes, right? The distance between the electrode, that is the length here, and the area of cross section. In the case of metallic wire, the area of cross section of the wire. In the case of electrolytic cell, it is the area of cross section of the electrodes, right? I think these are the basic concepts, and on the basis of this, we have derived this formula R is proportional to L upon A. I'm just reminding it. R it was proportional to L upon A. We have studied earlier, and just to remove this proportionality sign, we have used one proportionality constant. R is equal to rho L upon A, and this rho is called specific resistance, and I write the formula. This will be the terms of R into A upon L. If I make this area of cross section unit 1 centimeter square, and the length, the gap between the electrodes is 1 centimeter, the resistance offered is equal to specific resistance. In case of the electrolyte, I can assume it like if this is suppose a cubic a cube having the dimensions 1 centimeter length and a 1 centimeter breadth. How much solution can be filled in this cube? Suppose it's not 1 centimeter, I also know, but you have to imagine if this is a cube in which the solution is filled, its length is 1 centimeter, width is 1, height is 1. Whatever the volume is here, the that volume will be 1 cubic centimeter, and the resistance offered by the 1 cubic centimeter solution is called specific resistance or resistivity. How much resistance is offered by the solution that is filled in this 1 bar 1 cube that will be there, right? That will be called specific resistance or resistivity. I am repeating because the today's topic I have correlate with this term. And very important it is that you must understand. And I think now you can say that it's a constant value for any of the particular substance, right? When both the quantities L and A are unit, it is 1 centimeter and the A is 1 centimeter square. The R is equal to rho. That means now its rho value is there. R and rho are together. The rho is the resistance offered by the 1 cubic centimeter volume of the solution. In the case of matter, is the resistance offered by the 1 centimeter cube volume of the metallic wire. And one more important term I want to introduce here that we have not discussed earlier, the cell constant. One term is cell constant. You are not factored in now. If there is a cell, if suppose it is a cell, and this is the setup made. This distance, this is L, right? And the area of cross section of this is A. And for a particular cell, generally you don't change this cell. Where you have placed the electrodes, that remains at the same place throughout the experiment, and the area of cross section. You are not going to change frequently the electrodes. Whatever the electrodes you have used in the beginning, till the end you will use the same electrode. That means L is a constant and A is a constant for a particular observation, for a particular experiment. And this is called cell constant. This ratio, the ratio of L1A, this is called the cell constant. Since both the quantities are constant, the L and A both are constant, we call it the cell constant. Right? This term I have not taught you in the previous class. This is a new word that I am using here. So the terms that we have just revised is the resistance, conductance, resistivity, and the new term that we have studied is the cell constant. The very important term is cell constant, and here it's important because you have to correlate the conductivity with this one, right? What is conductivity? We have discussed in the previous class. Conductivity is the reciprocal of the resistivity. 1 by rho, right? The inverse of R. K is equal to 1 by rho, and from here the formula was equal to G or C. Any term you can use here, either the conductance, for the conductance, both the symbols are used, G as well as the C. The K was equal to G into L and K was equal to G into cell constant. Instead of this L A, I have just introduced with this term. This is cell parts. So this is just a quick review for the things that we have studied in the previous class. It was a revision session. Now I am coming to the next part of the class, the next part that we have to study. Two important terms we have to study today. One is the equivalent conductance, and the other term that we have to study, it is the molar conductance. Two terms we have to study. One is the equivalent and the other is the molar conductance. I think we better let's start with the molar conductance. You can understand this more conveniently, then I will go to the equivalent conductance. Molar conductance, that means the conductivity of one mole. If I have dissolved 1 mole of the solute, 1 mole of the electrolyte in any solution, whatever the conductance you will observe, that will be defined as the molar conductance. But my dear students, one thing I just want to point out here, don't take it that always and always the molarity of this solution will be 1. I am just coming one by one how you will understand this concept. It is, you all know that conductivity is because of the ions, right? And the conductivity that is offered by the how many ions, that much ion which are present in 1 mole, right? Whether the solution is 1 liter, 10 liter, 50 ml, irrespective to that, right? If this is a solution, right, that I have prepared, right? Suppose 1 mole of the copper sulfate is dissolved into it, right? If I am going to add some more water, right, then also the ions which are present here are not going to leave this space. No, definitely they will remain in this container only, in this beaker only, and they will conduct the electricity. Right? So irrespective to that, that will be the molar conductance. Molar conductance means the conductivity offered by the 1 mole of the electrolyte. Clear? If the number of moles which I have dissolved in the solution is 1, right? This will be called the molar conductance. The conductance of, please note it down, the definition better, I give you right with me, right? And absolute term. What is the absolute term? How you can define the molar conductance? Simple 8 mole electrolyte का जो भी conductance हो, right? The conductance offered by the volume of the solution that contains the volume. And this volume, it may be 1 cubic centimeter to uncountable or invisible 10 ml, then 100 ml, then 1 liter, 2 liter, 5 liter, depending upon that. But what should be constant? What should be fixed? The thing that must be fixed, it is the number of moles. Right? The number of ions you don't have to change. The number of ions will be 1 mole. Right? How many moles, how many particles are present? That means you can compare it with the Avogadro number. 1 mole of the electrolyte has the number of ions equal to the Avogadro number. The conductance offered by the Avogadro number of the ions is called molar conductance. Clear? And absolutely you cannot measure the value. The measurement of absolute value of this molar conductance is not possible, and we measure it in the terms of the specific conductance or conductivity. The K kappa. Right? What is the symbol for this? The symbol that we use for the molar conductance It is the cat M. कैट हमेशा देखिए शेप जो है वो कैट जैसा है, इससे आसान है इसको कैट से याद रखना. दिस इज द सिंबल दैट वी यूज फॉर द मोलर कंडक्टेंस, राइट. कैट एम, right, m is written in the subscript part here. So molar conductance means the conductance offered by the 1 mole of electrolyte. Here, I think now you all would have understand. This is the conductance of 1 mole of the electrolyte. Suppose I have the solution that right 1 cubic centimeter, right, and this has the 1 mole of the electrolyte. In this case, I think we just have discussed that the conductance of 1 cubic centimeter of the solution is K, conductivity. So here the molar conductance will be equal to conductivity. But suppose the things are not same. The 1 mole is dissolved in the 5 centimeter cube, or it is dissolved in the 10 liter, 2 liters of the solution. That means this will be now in this case when the 1 mole is not present in the unit volume of the solution. What you have to do, how you have to calculate, you have to multiply the K with the volume that has this much number of the moles. Now, this what the formula you will get, molar conductance will be equal to K into V. K, you all know, is the resistance conductivity, and this is the conductance offered by 1 cubic centimeter of the solution. Right? If V is the volume that contains the 1 mole of the electrolyte. Right? What is V here? V is the volume of the solution that contains 1 mole of the electrolyte. So definitely now this is the conductivity by the 1 cubic centimeter multiplied with the total number of the volume. This will be equal to the molar conductance of the solution. Right? And I hope you all remember the term molarity, normality and molality. What is molarity, dear students? Do you remember? I can see the students are there and they are learning. It's good to see you all. Molarity is the number of moles present in the unit volume of the solution. And I hope you all remember that this was M, okay, and molarity, this was equal to the number of moles divided by the V, the volume of the solution, right? The second chapter and the class 11. In both the case, I think some of the students must have learned it in the class 10th also. Representation of the solution is filled, right? So here, from here, can you substitute this value? Right, if C number of the moles, suppose C number of the moles are present in this volume, what will be the value of V? V will be equal to 1. So now I am coming to the conclusion. Right, coming to the formula, that is extremely important for the examination point of view, for the purpose of numericals. The molar conductance is equal to K 1 by C, and C is the number of moles. Please remember, C is the number of moles present in 1 liter volume of the solution. And if the volume is taken in the milliliter or the centimeter cube, this, I think we all remember the formula that we have used that time. C is the number of moles. Please do remember here, the C that I have used here, it is for the number of moles present, right, in the 1 liter. I have derived from this place from the definition of the molarity. So I think now you understood what is the molar conductance and how I have derived this formula. The conductance offered by the volume of the solution that contains the 1 mole number of the electrolyte. Right? Can any of you write the unit of the cap M, the molar conductance? Here, what is this? K. And its unit is, from this formula, we can go for the unit. What is the unit of K here? You all can see here, this is G or the conductance. That is cycle or mole. And here it is L upon K. Right? So from here, you can come to the conclusion, you can come to the unit, and just by substituting the unit here, you can find out the unit of molar conductance. And I hope you all will do and you all will write till discussing the topic equivalent conductance. Otherwise, I am as usual always there. If you are not able to write the unit, definitely I will tell you. But I just want that you go for a brainstorming session. Don't be a passive learner, right? Always an activity is required, right? How much active you will be in the class, that much you will learn. That's why I just want that you give some exercise to your brain also along with me, right? Here, there is nothing different. Only one thing is different. And rather than the 1 mole here we use 1 gram equivalent. And I think you all remember the relation between the gram equivalent and number of moles. Moles is equal to N into gram equivalent. And this N is most of the time valency and other terms. So many times we have discussed earlier also. So here the only difference in the molar conductance and the equivalent conductance is here it is the conductance offered by the 1 mole, and here it is conductance offered by the 1 gram. I am taking an example. HCl. If I absorb 36.5 gram of the HCl, right, in V volume of the solution, right, this V volume, how much conductance will offer, that will be molar conductance, right? In this case, the gram equivalent, the equivalent mass and the molar mass is same in the case of the HCl. So, if the 36.5 gram of the HCl has been taken, the equivalent conductance and the molar conductance will be same. But it will not be same in the case of the sulfuric acid. Right? If I take the sulfuric acid, right, H2SO4. This is the sulfuric acid. Its molar mass and equivalent mass are quite different from each other, right? They are different from each other. 98 is the molar mass of sulfuric acid, but the gram equivalent mass or equivalent mass is 98 divided by 2, and this 2 is the value of the N, and this is the number of hydrogen in the case of acid, in the case of base OH, and in the case of metals, it is the valence, right? So here this will be. So how many gram equivalents are present, right? So the conductance offered by the 1 gram equivalent, right? That will be the equivalent conductance represented by this tag EQ. What symbol we use? This is the symbol that we use for the equivalent conductance. Clearly, students? And similarly, this can also not be measured in the absolute term. Again, this is measured in the terms of the K or the conductivity, right? So K or conductivity, again you all know that K is the conductance offered by the unit volume of the solution, and if the volume is V, that carries the number of gram equivalent 1. If 1 gram equivalent of the electrolyte is dissolved in this V volume of the solution, what it will be? The equivalent conductance will be K into V. And similarly, as I have done for this, you can write again equivalent is equal to K into 1000 upon C, that you can see here, right? This is the part. The equivalent conductance is equal to K into V. K is the conductivity, V is the volume that contains 1 gram equivalent. Please note it down. This is the volume that contains 1 gram equivalent. It is not all the time 1 liter or 1 centimeter cube, right? This was the thing I was discussing in the beginning. That it is not the conductivity of one normality solution, or this is not the conductivity which has the molarity 1. It is the conductivity of the volume. What volume? The volume that has 1 mole. In the case of gram equivalent, it has the 1 gram equivalent. Clear? So that's why we need to account the volume V. I hope I'm clear to some extent to all of you. And now I'm coming to the next part. And if you have any doubt, I can discuss it. We will see the questions. Now I want to discuss what is the effect of dilution. Dilution is to lower the concentration, right? In last class also, the different factors, how they affect the conductance of the electrolyte I have discussed, and this term I asked that the effect of concentration I will take in the detail in the coming class, and this is the time. You all know that with the dilution, if the solution is becoming dilute, right, the concentration is decreasing, the concentration is lowering. What do you expect? The molar conductance, the equivalent conductance, and the K. Which will increase or which will decrease? Use कीजिए अपने brain को. As you are going to increase the dilution, that means the solution is becoming dilute. Okay, I have this solution, right? Now, what I'm going to do, I'm just going to take this much more amount of the water, this 50 ml water I have added more. Now in this condition, now at this stage, what will be the effect of this? Do you feel the conductance, molar conductance and the equivalent conductance and K? What you think will change? The very correct answer I am seeing here, the molar conductance will increase, right? I'm looking at upward mark. Same for the equivalent, but the K will decrease. The K is going to have a negative impact. Why? The K is the resistance conductivity of 1 cubic centimeter of 1 unit volume. And in this case, what you will see, I have diluted it. That means the number of moles, the number of ions present in the unit volume are going to decrease. Because of this reason, the K will also decrease. But dear students, both these quantities will increase. What this will happen in the case of the strong electrolyte? Strong electrolyte is that can easily dissociate. Their dissociation constant or the degree of dissociation is 100% dissociation we expect. What do you think? Okay, this is a solution, right? The Ca is the electrolyte that I have used, right? The cation C and the ion A. Likewise will be the arrangement, and definitely in this case, if it is cation, that means it is bearing the positive charge. It is the ion bearing the negative charge. Again, this is positive charge, this is the negative charge. Since already being this strong electrolyte, it is dissolved, it is ionized. The number of moles, the number of ions are large here. All the Ca is dissociated as C plus and A minus. The charge may vary 1, 2, 3, 4 depending upon the electrolyte. Okay, so here we are having one bond, right? Still they are bonded. That means they are not having the freedom of the movement. As we are going to dilute it, what you will see that now the distance between them is going to increase. The volume increase, that is definitely the distance will increase, and because of that, now the force that we experience, this force will become weak. And because of this, what you will observe, there is easiness, the freedom of flow. Now, speedily, the mobility of the ions is increased, and because of that, a strong electrolyte will also on dilution, right? If a strong electrolyte is there, this also on dilution shows greater or positive change in the conductance, both the molar conductance and the equivalent conductance. But since the on dilution, the number of ions in per unit volume decreases, the K decreases. Now I'm discussing the story of the weak one, right? In the case of weak, right, what happens? As you increase the dilution, as the dilute the solution will be, their ionization will be promoted. The concentrated solution, it does not has the 100% of the ionization, right? But as you are going to dilute it, right, what you will observe that every time, as now I have added the 50 ml of the water, if now I would have measured the conductivity, okay, it would have been increased for the weak electrolyte also, because the number of ions are more number of the molecules are now ionized. The weak electrolytes in the concentrated solution, they are not completely ionized. But as you are going to dilute it, what you will observe that the ionization will, electrolysis will increase, and definitely if the number of moles are going to increase of ions, definitely what will be the increase in the conductivity. But to what extent? Okay, suppose this is the solution, I added 50 ml and the conductivity was measured, suppose it was the 1.25. Now I have added one more 15. Okay, I shaped it, measured it, 125, maybe changed it to the 1.75. Again, what I did, I added one more 50 ml of the water, right? I have seen now it has become 2.5. But now I'm going to add some water. From 2.5 it is 2.6. But after a limit, okay, if now I'm going to add more water, what I will observe that what was the conductivity of that time is same as the 2.8. So I want to introduce a new term with this. This small exercise, this small experiment was to teach you what is the meaning of infinite dilution. The term infinite dilution does not mean that to add the infinite amount of the water. No, that you all know that infinite term does not exist actually, right? You all know that it is a hypothetical term. What is the infinite dilution? The dilution after which, if we are going to add more solvent, there is absolutely no change in the conductance. As I have shown you, right, in the beginning, I was adding the water, right, its conductance was increasing. But after a limit, right, after a limit, what happens if you add any more amount of the solvent? This is absolutely not going to change the conductance, and this is called conductance at infinite dilution, or this concentration at which if you are adding more amount of the solvent, you are not going to observe any change in the concentrate conductivity, right? That is called the infinite dilution, right? And whenever we are writing the conductance at infinite dilution, right? What the symbol you are using? This is the symbol for molar conductance and infinite dilution, and the symbol sometimes it is called limited conductance also, because now it's limited. Now the maximum limit, the upper limit, it has achieved. Now, whatever the changes you are going to make, this is not going to make any difference in the conductivity. That's what is also defined as the limited conductance or the conductance at infinite range. So I think, my dear students, you all can understand now the term infinite dilution does not mean that you add the infinite amount of the water. What is its meaning? The concentration at which, if you are going to dilute, okay, you are going to add any more amount of the solvent, the conductance is going to remain constant. Why? Because after a dilution, after that particular level, when it achieves, all the number of the moles which are present in the solution are ionized. Clear? So this is the meaning. And what was its importance? Why I taught this? What was the value? Why it was needed to teach you? Because I want to teach you the KOHLRAUSCH'S. I just want to bring you to the topic KOHLRAUSCH'S, and it was extremely important in the case of the KOHLRAUSCH'S. So I'm here just going for a quick review, okay? Just summarizing, then I'm going to go ahead. The rho, it is the resistivity offered, the resistance offered by 1 cubic centimeter of the conductance. The kappa is the conductance offered by the unit volume of the conductor, right? This is equal to conductance into the cell constant. The equivalent conductance, the conductance offered by the solution that has the number of moles equal to 1 gram equivalent. Molar conductance, the conductance of the solution that has the number of moles present in equal to 1. right? And infinite dilution is the concentration of the solution after which dilution is not going to alter the conductance of the electrolytic solution, right? And conductance observed at this particular concentration, this is called the molar conductance in the case of molar and infinite, and similarly in the case of equivalent conductance. This is called inconductance, equivalent conductance at the infinite dilution. Clear? Now, there is one important law that is called the KOHLRAUSCH'S. What KOHLRAUSCH'S did? KOHLRAUSCH'S has done the experiment on the conductivity and which type of the conductivity? The infinite, the conductivity of the solutions at infinite. Here I have prepared one table. You all can see here. Here, KCl and NaCl. These are the two electrolytes that has been taken by the KOHLRAUSCH'S. And what he has observed, he has experimentally observed that its molar conductance is 149.86 and 126.45 for the case of the NaCl. The difference of their conductivity is 20, and all these measurements have been taken at the 298 Kelvin. The temperature, the T is equal to 298 Kelvin. Clear? Here also, then earlier he has taken the chloride salt of sodium and potassium. In the next observation, he has taken the bromide salts of the sodium and potassium. Again, the same experiment he has performed, and he has observed, he has noted, calculated the value of the conductance at the infinite dilution, the molar conductance at the infinite. And again, what he has found that the difference in the conductance of KBr and NABr is the 23.41. Similarly, for the nitrates also, the KNO3 and NaNO3, he has done the experiment and he has observed that this difference is same 23.41. That means what you can see here in this set of the experiment, the CN is same, the anion is same, the difference is of cation. And here it is potassium, here it is sodium. Again here the set is same. The different set that it is the sodium and potassium. Similarly, in the case of KNO3 and NaNO3 also, the difference was in the sodium and potassium, and the conductance difference was also same. That means what he has come to the conclusion that every cation and every anion has its own conductance, right? The value of its conductance is constant and definite is the conductance of every. Now what he did? He thought maybe if the cation is same, but the difference is cation, the anion is same. Maybe the things vary if this thing is changed. So what he did, he just wanted to make the things very confirmed one. So what he has done, in this case, the anion was same, and in this case, what he has done, he has kept the cation same. Now KBr and the KCl. In both the thing, what is the common? That is the potassium that is common here. And he has found that the difference is 2.06 unit. Similarly, he has done for the sodium bromide and sodium chloride 2.06. So here, what are the things say? The cation is same, that means its contribution is same. How much it is contributing in the case of the NABr, the same it is contributing to the NaCl. But the difference is in the contribution of bromide and the chloride. And both the cases, whether it is taken with the potassium or whether it is taken in combination with the sodium, The difference is same. So what conclusion he has come? He has come to the conclusion that every ion, right, has its independent value of the conductance, the molar conductance at infinite dilution, right? And the sum of the ions conductance is the molar conductance of the, suppose there is AXBY. This is the electrolyte I have taken, right? According to the Kohlrausch, what Kohlrausch says that A and B, they have their own conductance and their conductance does not depend upon each other. Like here you can see the Cl, whatever was its conductance with the potassium, the same was with the sodium. Here also, whatever was the conductance of potassium with bromine, the same is conductance with the chloride ion. That means all the ions have their independent value. They do not depend upon each other. If I take the sodium sulfate and the potassium sulfate, it's not like that. The sulfate will change its conductance with the sodium and potassium. No, it's not relative value, it's the absolute value. This is the thing that I want to say here. And what the conclusion was given by the Kohlrausch, that every ion has its own independent conductance value at infinite dilution, and the conductance of the electrolyte is equal to the sum of conductance of the constituting ions. Here, AXBY, okay, this is the electrolyte I have taken. This electrolyte, how much molar conductance it will offer? It will offer the conductance equal to the x number of A plus conductance of offered by y number of the B. I am taking one more example with all of you. I am taking the example of HCl. The conductance, the molar conductance at infinite dilution of HCl will be equal to the molar conductance of hydrogen ion H plus at infinite dilution and molar conductance of Cl minus. Now I am taking another example, H2SO4. Molar conductance of sulfuric acid, this will be equal to, here you can see how many hydrogens are there? 2. So it will be equal to 2 into the molar conductance of H plus ion plus molar conductance of sulfate ion and infinite dilution. This is the conclusion that the Kohlrausch has given. So what he says that every ion has the independent value of the molar conductance at infinite dilution, and same is the concept for the equivalent concept of it. Both the terms you can use molar as well as the equivalent, right? And the total, the electrolyte, that is how much the conductance will be of the electrolyte, that will be equal to the sum of the conductance of constituting ions. And my dear students, the importance, the beauty of this Kohlrausch is for calculation. It has its application part is very, very important here. The strong electrolytes, since they are ionizing easily, you can find out, you can calculate its conductance by the experimental setup. But since you all know that weak electrolytes, they do not show this ability, right? And because of that, we can use an indirect method, right? So this indirect method is given with the help of Kohlrausch law that we will learn in the coming session, and I hope you will do the exercise and learn the topic that we have discussed. Next we will hope for the next one.